Alright, so in this lesson we're going to start talking about electrostatics. What's true about electrostatics, what we're looking at here is distributions of charged particles or electrical charges which are not moving. That's where the term electrostatic really comes from. And we'll look at electrostatics first, and then we'll get into electrodynamics, generally viewed at, or what we would generally look at as circuits next. Charge is the basic unit that we use in electrostatics. One thing to point out is that charge is not a base unit in the SI system. It happens to work out that electrical current is a base unit. We'll talk about that a little bit later on, why that is. The unit of charge is the coulomb. It happens to work out that a coulomb is a pretty large quantity of charge. As you are probably aware, really from about, middle school on, there are objects within an atom called electrons and protons, these little tiny particles that contain charge. It happens to work out that the electron and the proton have the same magnitude of charge, 1.602 times 10 to the negative 19th coulombs. The electron is negatively charged and the proton is positively charged. Matter becomes electrically charged when it either gives up or takes in electrons. So the transfer of electrons in matter can take something that was neutral originally and turn it into either a negative charge or a positive charge, depending on whether you've gained electrons or lost electrons in that matter. So this also leads to a last kind of idea that charge is one of these quantities which we would call quantized. What that means is it's a fancy way to say is that only certain values of charge that are allowed, and those values happen to be multiples of the charge of an electron. This fact is actually one way that you can work backwards to find the charge of an electron through an experiment called the Millikan oil drop experiment. Look it up, it's pretty cool. It's a neat way to find the charge of an electron. So let's look at what the effect of charge is. So if I take a glass rod and rub it with silk and suspend it from a string, and then say I take a second glass rod, also rub it with silk, as shown in part A, and bring the second glass rod to the first glass rod, what you would notice is the two rods happen to repel one another. I'm able to move the suspended glass rod away from the other glass rod without actually touching the two rods together. This may look like magic, but there's no magic going on here. We really have a force at a distance happening that one of the glass rods is putting a force on that the glass rod that I'm holding is putting a force on the glass rod that's being suspended. Now if I did the same thing with a plastic rod and rubbed it with fur and brought it close to the glass rod, what I notice is I'm able to attract the glass rod to the plastic rod. Again, this will look like magic, but really there's no magic going on here. This is just action at a distance, that I have a force acting between the two rods. It's an attractive force. So what's going on here? What I've really done is I've given the glass rod, when I rub it with silk, a positive net charge. I've basically removed electrons from the surface of the glass rod. So when I have two positively charged objects, those are two like charges, they repel from one another. Now, when I rub the plastic rod with silk, what's happened is I've deposited, the plastic rod with fur, I've deposited additional electrons onto the plastic rod. So I have a positively charged thing next to a negatively charged thing. And so I get an attractive force. Opposites attract. Now the one thing to point out about electrically neutral objects that do not have a positive or negative net charge, is that they must have a net charge of 0. It is not accurate to say electrically neutral objects have no charge, because we know they must have charges. If you think back to your chemistry, you know atoms contain protons and electrons, and therefore if an atom is electrically neutral, the number of protons and the number of electrons must be equal. If an atom is positively charged, or what we call a positive ion or cation, we know we've lost electrons. If it's negatively charged, a negative ion or an anion, we know we've gained additional electrons. So you can actually use some of what you've probably learned in chemistry, maybe even back in like middle school physical science, about how atoms work, to think about how charges work. So the second demo that I want to talk about, and I hope to do both of these demos in class, it kind of depends upon a few different factors, one of them being weather. As odd as this will sound, these demos work really well when the relative humidity in the air is very low. And so if we get a good, cold, dry day, these demos work very well in a good, cold, dry day. They do not work very well in a warm, humid day. So this other one, I have a glass jar, and it's sealed up, and sticking out of this glass jar is a metal ball that's connected to a metal rod which connects to two pieces of gold foil down there. The reason why I've picked metal all in here is that metal happens to be a very good conductor of electricity. What that means is the electrical charges will flow easily through that substance. That I'm able to move electric charges to and from very easily in that substance. So what happens if I have this electrically neutral object if I bring a positively net charged object, maybe that glass rod that was rubbed with silk close by? What you see is that the foils separate. The question is, why does that happen? Well, why does that happen? Well, the positively charged object attracted negative charges up to that metal ball. It also did a second thing. It repelled positive charges down as far away as they can get from that positively charged rod, which is down in the foil. And so what you end up with is two positively charged pieces of foil that then can repel one another. This is an example of what we call charging by induction. Basically, I've induced a negative charge on the glass ball by bringing a positively charged object close by, and I've induced a positive charge in the foils by bringing that positive charged object close to the negative charged object. Now what happens if I reverse this? Well, guess what? As you might guess, we get the positive charges moving to the glass ball, the negative charges moving to the opposite direction, the foils separate. Same exact explanation, only opposite charges. The negatively charged object attracts the positive charges to the ball, repels the negative charges down in the foil, and they separate. So in each case, the charged object induces a charge on each side of the metal. We would actually technically call this an induced dipole because you have both a positively charged end and a negatively charged end that's being induced by another charged object being close by. Now if we did something like took a wire and connected it here and connected it to, say, somewhere like a metal rod that connects to the ground, what you'd ultimately end up with is a positively charged metal object when we work this out. Sorry, not sure why that happened. So some terminology that you might have. When we talk about a conductor, these are substances that allow charges to move easily through them. If we're talking about a conducting object, usually we find net charges along the outside surfaces of that. The reason for that is very, very simple, that charges want to be as far away from one another as possible, and the distribution which maximizes the distance between them is on the outside surface. In an insulator, this is a substance that does not allow charge to move easily through it. Something like plastic or glass. These are ones that have some resistance to the flow of charges. Charging by contact. This is a way of charging by physically touching an object to another object, that you can transfer charges in that way. Charging by induction is where you create a net charge on an object by either the attraction or repulsion interaction from other charged objects nearby. So let's do a quick example here. Let's do a quick problem or a quick thought exercise. And so we're going to take two metal spheres of equal size, and one has a net charge of 50 millicoulombs, and one has a net charge of negative 20 millicoulombs. What I'm going to do is take these two charges, touch them together, and then separate them, and figure out what is the net charge on either sphere after they've been touched together and separated. So what happens when we touch them together is that charges transfer, and the net charge on both objects combined happens to be 30 millicoulombs. Well, when you separate them, half of those charged particles end up on one sphere, half of them end up on the other sphere. They want to be as far away from one another as possible. So you end up with two charges of 15 millicoulombs. Now, if these were two plastic balls or two rubber balls, this may not work because the charges are not free to flow around the balls. If these are two metal balls, which is true, it'll work almost instantaneously. So I said that electric current happens to be the base unit in the SI system. The reason why it's the base unit in the SI system is the electric current is something that's really easy to measure, that anyone in any lab has a technique to measure. Unlike electric charge, which, well, actually takes a lot of work to measure. It's actually fairly difficult. It's almost easier to measure electric current and time to get electric charge than it is the other way around. So the relationship between current and charge, current happens to be measured in the unit of amperes, is that you can think of current as the rate at which charge moves, or the time derivative of charge. Kind of similar to the relationship between position and velocity, same relationship between charge and current. And so here are two ways that we can write charge versus electric current. I've got it in the integral form on the left and in the derivative form on the right. I believe on your equation sheet it probably gives it to you in the derivative form that is shown on the right. Let me double check that for you. The answer is it does give you it in the derivative form as shown on the right. So let's do a quick problem, and let's say we have a light bulb that's using 0.25 amps of current for 30 seconds. Now an amp, if we wanted to define it in terms of coulombs and seconds, an amp is really 1 coulomb per second, or you can think of a coulomb as 1 amp times 1 second. Probably more accurate to think of that second one, that a coulomb is an amp second. So we want to figure out how much charge passes through the light bulb, and then how many electrons must have passed through the light bulb. Well, the way to figure out how much charge is pretty easy. Current times time, 7.5 coulombs. And then we just need to do a quick unit conversion to get that to numbers of electrons. Remember that the magnitude of the charge of an electron is 1.602 times 10 to the negative 19th coulombs. If we do a unit conversion, you find that 4.7 times 10 to the negative 19th electrons had to pass through that light bulb in order for it to be lit up for 30 seconds with a 0.25 amp current. So that's kind of a quick overview of some introduction stuff to electrostatics. In the next lesson, we'll look at Coulomb's law. How do we measure this force of attraction or repulsion? And what are some things that we can think about when we go to measure those forces?